double integral r e to the power of x plus y divided by x minus y, okay, where r is trapezoid with vertices 1, 0, 2, 0, 0 minus 2, 0 minus 1. Okay. So let's have a look at the region firstly. So we have points 1, 0, and 2, 0. We have 0 minus 2 and 0 minus 1. So we're talking about this region. Okay. So the substitution which we kind of want to do is you have, if you look at our function, then you see x plus y and x minus y. You also, if you look at our region, then let's have a look. So for example, if you look at this line, slope equals to 1. Slope of this one line equals to 1. So both lines are going to look similar. So y equals intercept, y-intercept negative 2, so x minus 2. Y-intercept is negative 1 for top line, so y equals to x minus 1. So y equals x minus 1 and y equals to x minus 2. So from here we can get y minus x equals to, I guess it will be better x minus y to have positive number. So we have x minus y equals to 1 and x minus y equals to 2. So that's kind of suggests that if we want to do substitution, then the substitution which I will want to do is x minus y, y equals to u. At least that's for 1. Okay. And again, I kind of want to do substitution. The reason for that is because if I look at my region, it's neither type 1 nor type 2 region, so I have to break it into pieces. So I want to make it into something more simplistic in that sense. Okay. So if I do that, I'm going to get my first going to be u equals to x minus y. Okay. Second one will come from my function, because if I look inside of integral, I see x plus y. So that's kind of suggests maybe I want to have one of them to be so at least in my notation, I call this on v. It doesn't matter much. And I'm going to call u to be x plus y. Okay. And u equals x plus y, and the reason where it's coming from, because we have a look at the function which you integrate. You have x plus y in the exponent, x plus y over x minus y. Okay. So let's figure out what's going on here. So far we did x and y. So we did u equals x plus y, v equals x minus y. So from here we're going to get u plus v equals to 2x. So x equals to u plus v over 2. And we have u minus v equals to 2y, so y equals to u minus v over 2. Okay, so let's plot this line, this boundary. our original boundary is x equals 0. That means x equals to u plus v over 2, which means u plus v over 2 equals to 0, which means u plus v equals to 0, which means u equals to negative v. That boundary is u equals to negative v. This boundary is, so let's see what that means. That boundary is x equals to 0. And x equals to 0 means u plus v over 2 equals to 0 in terms of u and v. So we have u plus, sorry, I didn't mean to say it's y equals to 0, right? And y equals to 0 means u minus v equals to 0. Minus here, we have u minus v equals to 0, so u equals to v. All right, so I'll copy it one more time on next page. So what we've got. So our original one was x minus y equals to 2. And x minus y, we called it as v. So we're going to get v equals to 2 for this one. This one was x minus y equals to 0. In terms of u and v, that's v equals to 0. That one was y equals to 0. And y equals to 0, we just did a second ago. It was given as u equals to v. This one was x equals to 0, and it's going to give us u equals to negative v. So now we got new boundaries in terms of u and v. Let's draw them. To draw new boundaries. So we're going to get v equals 2 and v equals to over 1. Oops, sorry. That was x minus 1, no, not equals to 0, it equals to 1, right? Because we'll intercept. So we'll intercept is 1. So we're going to get v equals to 1, v equals to 2. Okay. 1 and 2. Then we are going to have u equals to v. And we're going to have u equals to negative v. Okay. U equals to v, u equals negative v. And that's the region we are talking about right here. Okay. And if you look at this region, that is your kind of type 2 region because you want to go left to right, left to right, left to right. So type 2 region. So we clearly see that v on outside will be changing from 1 to 2, and u will be changing from left, which is negative v, to right, which is v. So it's the limit form of integration. Recall that u equals to x plus y, v equals to x minus y. So instead of calculating straightforward, I do Jacobian from u to x and y. So I'm going to get 1, 1, 1 minus 1. So I'm going to get negative 2. So then Jacobian from x, y to u and v, and actually I'm going to take absolute value of it. It's going to be absolute value of, and I have to take reciprocal of what I just did. But don't forget that's reciprocal, so going to be 1/2. And that's going to be our price. Price to pay to switch from X, Y to U and V. And the rest is kind of straightforward because now we're going to have our integral e to x plus y over x minus y dA. That's our original one. Now we're ready to switch. X plus y is u, x minus y is v, 1/2 u dv. U is changing from negative v to v. V is changing from 1 to 2. And that's how we set integral. Set up integral. And integral itself is not too bad. To 2. We're taking derivative with respect to u, so we do substitution, z equals to u over v. Do it, so you're going to get extra v in front. So v times e to the u over v. U is changing from negative v to u equals to v. So we're going to, I forget 1/2 somewhere here. So we'll get 1/2 integral 1 to 2. Substituting lower bound, substituting the upper bound. So we're going to get v times, substituting v, we're going to get e, substituting negative e, we're going to get negative 1. V. So it's again straightforward. 1/2 e minus e to the negative 1. Antiderivative of v is v squared over 2. We're doing it from 1 to 2. So final answer is going to be 3/4 e minus e to the negative 1. So after we got our substitution, the integral itself is not too bad. So let's see, we have the following regions. So we have x squared minus y squared equals to number, x squared minus y squared equals to different number, then xy equals to number, and xy equals to different number. So x squared minus y squared equals to number, and x times y equals to number. So that's how it are. So it's bounded by x squared minus y squared equals to 1. And x squared minus y squared equals to 4. And by xy equals to 3. And xy equals to 1. So just looking at this region, you almost immediately know the substitution which you want to do is u equals x squared minus y squared, and v equals x times y. That's almost immediate. Now, if I want to find Jacobian for this one, I don't want to find x and y in terms of u and v. I mean, it's possible, but it will take a little bit more time than I want. So maybe I'll do it when I need to. So anyhow, but instead I will do from u, v to x, y. So I'm going to get 2x minus 2y, and then y, and then x. So we're going to get 2x squared plus 2y squared. So 2 times x squared plus y squared. Okay. Now price to pay from xy to uv is going to be 1 over what we just got. And if needed, take absolute value of that expression. And to get what will be x squared plus y squared in terms of x and y. So let me try. So we wonder what is x squared plus y squared equals to in terms of u and v. And we have u equals to xy and v equals to. So we want to get x squared and y squared. So that's the reason we're going to try to square u. So u squared is going to be x squared, y squared. Then we kind of try to get something going on with v equals x squared minus y squared. We kind of squared u, so why not just square v to see what's going to happen? And what we're going to get is x squared squared plus y to the fourth. So we're going to get v squared equals to x to the fourth minus 2x squared y squared plus y to the fourth. So which equals x to the fourth plus y to the fourth minus, and x squared times y squared is u squared minus 2u squared. Here we have x squared plus y squared. And if I square it, same way as I squared x squared minus y squared, I'm going to get x to the fourth plus 2x squared y squared plus y to the fourth. So that is x to the fourth plus y to the fourth plus 2u squared. Now if we look this one and that one, then we notice that x squared plus y squared squared is that top equation, x to the fourth plus y to the fourth minus 2u squared. And to balance it, we need to put an extra 4u squared. And that expression is v squared. So finally, we get x squared plus y squared equals to square root of v squared plus 4u squared. So sometimes, often, it's not easy to find. You see what kind of u is in v are supposed to be, but it's not easy to find and solve for x and y in terms of u and v, because functions are usually not straightforward, not linear. So we'll need to put some effort, some algebra to figure out what is going on. So anyhow, for our purposes, what we've got is Jacobian is from xy to u v was equal to 1/2 x squared plus y squared. And we figure out that that's 1/2 square root of v squared plus 4 squared. Okay. Now just imagine if we want to calculate double integral over the region R, right? X squared plus y squared dA. Then we're going to get double integral R, x squared plus y squared du. I don't want to keep it this way. What you notice in this case is we actually did not need for this integral to switch to a form of Jacobian in terms of u and v. We might have kept it as the original one, or 2x squared plus y squared because of reduction. So actually we did not need it to do it. Okay. So we did it anyhow, just to illustrate you that sometimes it's difficult, but for purposes of this one, we did not actually need it because our integral function was very nice. If integral function will be just x squared or y squared or just x plus y, then we'll have to do that. And limit of integration, you remember we had x squared minus y squared equals to 1, x squared minus y squared equals to 4. So we have b is changing from 1 to 4. U was equals x times y, and our limits x times y equals to 3, x times y equals to 1, so we have 1 to 3. So in this case, we get easy integral 1 to 4, 1 to 3, 1/2 du. Split it. So we're going to get 1/2 times 4 times line 1/2 times 3 times 2. So we're going to get 3 is a final answer.